in the last unit, we discussed transformations that were rigid motions. And remember, a rigid motion is a transformation, or are transformations that do not change the size or shape of a figure. It just changes its location. Okay, so it keeps the shape exactly how it is, it just moves it to another spot for the plane. Okay? In this unit, we're going to talk about a new type of transformation called a dilation. And a dilation changes the size of a figure, making it bigger or smaller, but keeps its shape. So you might start out with a triangle, a small triangle, and then you do a dilation and it makes it a big triangle. But it's still the same triangle, it's just bigger or smaller. Okay? So true or false, a dilation is a rigid motion. Look what we just talked about, that rigid motion. False. Why is it false? Because very good. It changes the size of the figure. So a dilation is not a rigid motion. Translations, reflections, and rotations are all rigid motions. Dilations are not. So I was talking about it in a different unit. Rigid motions create figures that are congruent because it doesn't change the size. So the starting figure, the original figure, and the new figure are going to be congruent to each other. Okay? Meaning all the corresponding sides and angles are the same. The pre-image and image are always congruent to each other whenever you do a rigid motion. So whenever you do a reflection, a translation, or a rotation, the image and the pre-image will always be congruent to each other. Okay? And the diagram below shows an example of a translation, which is a rigid motion. Okay? If you can see, the figures are exactly the same. You just moved it over a little bit after you did your translation. We're going to state what we know about the corresponding angles and sides. Well, we know these figures are congruent. We know the corresponding angles are also congruent. They're the same. So we know angle G is congruent to angle G prime. The original angle is the same as the new angle. Nothing changed there. Okay? We know angle T is congruent to angle T prime. Nothing changed there. This angle and this angle are the same. They just changed locations. And we also know that angle B is congruent to angle B prime. Again, nothing changed. Those angles are exactly the same. The two figures are congruent. The sides, the corresponding sides, are also the same. And remember, corresponding just means, we talked about this a little bit, they're in the same spot. They match up. They're in the same spot of the two different triangles. So we know that side GB is congruent to side G prime B prime. They're in the corresponding spot of the triangles. They're the same. And you can even count and see that they're the same. GB is 1, 2, 3, 4. G prime B prime is 1, 2, 3, 4. They're the same length. Because again, you didn't change the size, you just changed its location. Didn't change anything about it. We also know GT is congruent to G prime T prime. And we also know side BT is congruent to B prime T prime. These two sides are the same, these two sides are the same, and these two sides are the same. Nothing changed from the pre-image to the image. Just its location. All the angles will be the same, all sides will still be the same. Questions over that? Okay. A dilation creates figures that are similar. So rigid motions create congruent figures. Dilations produce similar figures. Okay? Similar figures have corresponding angles that are congruent. That's still true. Their angles are still going to be the same. Okay? But the sides are different because we changed the sides. The sides are going to be what we call proportional. Meaning the ratios of the corresponding sides are going to be the same. So if you take the image You do that for all the sides of the figure, you'll get the same exact fraction. Okay? That's what that means. When you make a fraction of all the sides, you get the same exact fraction. Okay? When performing a dilation, the pre-image and image will always be similar to each other. So rigid motions, the pre-image and image are congruent, because nothing changed, just the location. Dilations, the pre-image and image are similar, because we changed the size. So the angles will be the same, but the sides will be proportional. We take a look here. This is an example of a dilation. As you can see, we had our original figure, our pre-image, and we shrunk it, okay, to get our image. We're going to state what we know about the angles and sides. Well, if we did a dilation, that means the pre-image and image are similar. So what do we know about the angles? The angles are what? The same, they're congruent. So angle A is still congruent to angle A prime. They're the same exact measurement. We didn't make anything wider, we just shrunk down the length of the side. So the width of each angle stayed the same. Angle P is still congruent to angle P prime. Angle L is still congruent to angle L prime. And angle J is still congruent to angle J prime. The angles did not change, but the sides did. So are we going to say that the sides are congruent to each other? No. What did we say the sides were when they're similar? That fancy word, proportional. So what that means, and when we do this, we always do image over pre-image. Okay, we always do tick mark over non-tick mark. Okay. Just the rule of having to write this. That means if we take the length of P prime L prime and put it over the length of its corresponding side in the image, PL, whatever that fraction is equal to after you simplify, it will be the same exact fraction of A prime P prime over AP. Those fractions will be exactly the same. That's what it means to be proportional. Those two fractions will also be the same as L prime over J prime, or L prime over LJ. Okay? All three of those fractions will be the same after you simplify. Okay? And then A prime, J prime, all four of those fractions will be the same. So if we take a look at P prime and L prime, because those are my flat sides, that's easy to find. The distance of P prime L prime is 0.5, and the distance of PL is 2. When you simplify that, that means it's 1/4. Okay? So this side is 1/4. When you make that ratio, this one will be 1/4, and that one will be 1/4 when you put all the distances into a fraction. Okay? That's what that means to be proportional. Fractions will be the same. Questions? You flip it over. The ratio of the sides of similar figures is called the scale factor. So if you can keep your paper flipped. I'm going to put back here. So we put P prime over PL and got 1/4 when we did that. That means 1/4 is our scale factor. We use the scale factor to enlarge or reduce the size of a figure when performing a dilation. When the scale factor is less than 1, the figure will become smaller, which is what we call a reduction. When the scale factor is greater than 1, the figure will become larger, which we formally call an enlargement. When asked to transform a figure by a dilation, it will sometimes be written like a sentence. You might see it like, dilate the figure by a scale factor of 4. Written sentence. Okay, kind of no-brainer there. But sometimes it will be written in this notation, which often gets confused with translations. The translations have similar notation. Okay? But in a translations notation, we would be adding or subtracting numbers from x and y. What are we doing with x and y in this notation? When a number is written right next to a variable, what operation are we technically doing? Adding those together, dividing. What are we doing with like the 4 and the x? We're multiplying, right? So when you have a dilation, the numbers will be in front of the variables. We're multiplying them together. Okay? Translations, it'd be like x plus 4, y plus 4. That would be an example of a translation. This is a dilation because the numbers are in front of the variables. Okay? And the scale factor is what's in front of x and y. And that's precisely what you do when you do a dilation. Okay? When performing a dilation, all you do is just multiply the vertices by the scale factor. And that's what it's telling you to do right there. Multiply all the x's by 4, multiply all the y values by 4. Okay. So if we take a look at this example, we want to graph the image of the following figures using the given transformations. Okay. Well, if we look at A, I have this notation, I have 2x, 2y. So that's telling me I'm doing a dilation. So similar to what we do with rotations, I like to write down all the original points. So x at -2, 0. P is at -1, -1. And V is at 2, 2. And what did we just say we do with our pre-image points to get our image points? What's our scale factor here in this problem? 2. Yeah, it's the number that's in front of the x and the y. Our scale factor is 2. What do we have to do with the original points in our scale factor to get our new points? Okay. Times them. Yeah, that's all you're doing. You just multiply. So you multiply this entire point by 2. So -2 times 2 is what? 0 times 2 is? -1 times 2 is what? So these are both going to be -2. 2 times 2 is 4. So these are both going to be 4. You multiply all the x's by 2, and you multiply all the y's by 2. And you're done. You just have to plot your new points. So we're going to plot -4, 0, -2, -2, and 4, 4. And there we go, we did a dilation. What happened to the figure? Did it get bigger or smaller? Bigger. What did you notice about the scale factor? Was it bigger than 1 or smaller than 1? Bigger than 1. So if you did this and you got a smaller figure, go back and check your work. It's supposed to get bigger. Okay? Think of it, we doubled its size. For B, now we're doing a dilation. What's our scale factor for B? What's our scale factor? What's the number in front of x? 1. 1/3. Okay? Circles are a little bit different when we dilate a circle. Any other figure, you do exactly what we did here in A. Circles, we always dilate about its center. Every other figure we dilate, we're always dilating about the origin. Meaning the origin stays exactly where it's at, and we're dilating around it. Okay? With circles, we dilate about its center. So the dot that's in the middle, that guy is going to stay exactly where it's at. It doesn't move. You don't multiply, you don't do anything to the center. What you're going to do is take these whole number points. It's almost like you make a T with the center, and you write those down, and you multiply those 4 points, just like we did with that. Okay, so I'm going to write down this point, 1, -1. No, don't do that. don't do that. Sorry. I thought I was trying something different than I did first period, but it didn't work out. It worked out for some. Hold on. No, don't do that. That doesn't work. Okay. I was trying a different method, and then I thought it would work, and it doesn't. Don't do that. We'll go back to what we did first period. Okay. The center is still going to stay exactly where it's at. Okay? Don't move it. But what you're going to do, you have to figure out, well, what is the radius? Okay? What? I'm losing my book. What do you remember is the radius when you look at a circle? Does anyone remember what that is?
It's like from like the side to the center.
Yeah, from the side to the center, and the center to the side. So you count that. What was the length of that radius? Okay. So what you're going to do to dilate a circle, you figure out what that radius is, which is 3, and you multiply it by its scale factor. Scale factor was 1/3. What is 3 times 1/3? 1. Okay, that's the new radius. So you're going to go back to the center, and instead of counting 3, you just count 1. But there's multiple radii, so you go 1 to the right, 1 up, 1 left, 1 down from the center. And you can. So that's how you dilate circles. Questions over that? Okay, with a circle, losing my voice. You just count the radius, go start at the center, count till you get to the edge here, and then multiply by the scale factor, that becomes your new radius. So you go back to the center, you count 1, 2, 1, 1, 1. Then you connect them to the circle. Questions over that? We'll skip that one. We'll come back to it tomorrow. Number 3 says, from example 1, do the slope of the pre-image and the image change? So let's see. Let's find the slope of FV. Okay. And when in the coordinate plane, how do we find slope? Something over something. Rise over run. See, just count. So if we're finding the slope of FV, what's our rise? We went up how far? 2. We went up 2, so it's positive 2. What's our run? 4. And we went right 4. So it would be positive 2 over positive 4. Okay. Well, let's find the slope of V prime, F prime, V prime. The image. What's our rise? We went up 4. What's our run? And we went up and right, so it's going to be positive as well. So we went up 4 over 8. Here's the thing. What do we have to do with our fractions? Simplify them. What does 2 over 4 simplify down to? 1/2. What does 4 over 8 simplify down to? 1/2. If you didn't simplify, you would have gotten the wrong answer. So we have to simplify. Did the slopes change? No. They stayed the same. Okay. They stayed the same. This is true for all dilations. Okay. Whenever you do a dilation, the slope of the pre-image and image through the original figure and the new figure will always be the same. As long as you don't do another rotation with a dilation. So if you dilate a figure and then rotate it, obviously the slopes are going to be different if you change the orientation. But if you just strictly do a dilation, these slopes will always be the same. This means the corresponding sides of the pre-image and image will also be what to each other? What types of lines have the same slope? You may know what they called?
Parallel.
Parallel, very good. Now, so the pre-image and image, when you just do a dilation, are always going to be parallel to each other. out, they will never intersect. It might look like they do if they're close, really, really close. It's just human error in trying to draw the straight line. Accidentally intersect. But they'll never touch. They'll always be parallel. Questions over that? Okay, got two more. Sorry, notes are just closed. So 4. We are going to write the equation of a line, y equals 6x minus 8, after it's been dilated by a scale factor of 1/2. Okay? Well, we just said the image, or the pre-image and the image, when we do a dilation, are parallel to each other. So this original line and the new line after we do a dilation are also going to be parallel to each other. And what do we know about parallel lines and their slopes? We just said it. They're the same. So if the slope of the original line is 6, what's the slope of our new line going to be? 6. I know that part. So whenever you're dilating a line, the slope of the original figure will be the same as your new line. Because they're parallel. Slope didn't change. We just found that out when we do a dilation. But what about the y-intercept? Does the y-intercept change? Yeah. Because we look back, you don't have to flip, I'll flip back on the thing. When we look here, technically, every single point on FV was dilated by a scale factor of 2. You multiplied every single point on that line by 2. But just to make our lives easier, we just multiply the vertexes in time. Okay? So every single point on this line gets multiplied by the scale factor. And the y-intercept is a point on that line. So all you have to do to figure out what your new b is, take the original b and multiply it by whatever the scale factor is. So we're going to take negative 8, because it's a negative, multiply it by the scale factor. And what do we get when we do negative 8 times 1/2? Negative 4. That's your new b. Okay? So whenever you're dilating a line and you need to find the new equation, you keep the slope exactly the same, just multiply the y-intercept by the scale factor, and there's your new equation. Okay. If we take a look at this last one, we want to write the slope and y-intercept of the line 9x plus 3y equals 5. What's the problem here? What? Has x and y, right? Y is not by itself. It's not in y equals mx plus b form. So we can't tell what the slope is. We can't tell what the y-intercept is. So what do you think we have to do to get it in y equals mx plus b form? Okay, move the x over, solve for y. So if we have a positive 9x, how are we going to move it over? Subtract it. So we get 3y is equal to negative 9x plus 5. Then what do we have to do with the 3? To get y by itself. We have to y. So when we divide by 3, we get y is equal to, what's negative 9 divided by 3? Negative 3. Is 5 divisible by 3? Is 3 going to 5 evenly? No. So just leave it like that. Don't even worry about if you could simplify. Don't even worry about simplifying. Just leave it as 5/3. Okay? It's weird, I know, but leave it. Okay? And then it's the exact same process we did with example 4. All right? Let's write the new equation. Y equals, what's the slope of our new equation going to be? Negative 3. Yeah, the slopes don't change. Whatever the slope of the new equation is, that's what's going to be the slope. The slope of the old equation, that's what the slope of the new equation is going to be. And then what did we say we do with the y-intercept to find our new b? Times it by the scale factor. So we have to do 5/3 times 6. And what's 5/3 times 6? 10. Plus 10. Okay? But it didn't want the equation, they wanted the slope and the y-intercept. I needed to really have to write the equation, just for more practice I did. And we said the slope was -3, the number in front of the x, and the y-intercept is the number in the back. Questions over that? Okay, rest of the task is yours. There are a few minutes left. Sorry, I try not to make notes that long. It's just how things happen.